welcome you all here in my lecture number 35, that is longitudinal dimensional stability derivatives. I have covered 34 lessons before, and now I am in the process of the next lesson. In this lecture, I am going to cover the following topic, that is longitudinal dimensional derivatives, then longitudinal dynamics state equation, Laplace transform, and longitudinal characteristics equations. In this lecture, I am going to answer few questions like what is the longitudinal derivatives, how to use Laplace transform to solve flight dynamic problems of aircraft, how to find dynamic stability through characteristic equations. These problems I am going to discuss in this class, and we are going to understand and get the answers of these questions. Here, before I go, I have already discussed about few things like the different derivatives which are I am going to discuss here. So here a small perturbation theory is going on, and from last few classes we have discussed about these theories. The equations which are given here are mu dot is equal to minus mg cos theta 1 plus fx. This is the force equation for x direction. Next equation of motion is m w dot minus u1q is equal to minus mg theta sin theta 1 plus fz. This is the force in z direction, means up or down. And third is the Iyy q dot is equal to m, where capital M is a moment and Iyy is the moment of inertia with respect to the y axis. Q dot is a pitch rate, and u dot is a velocity rate in x direction, and w dot is velocity rate, means acceleration. These are all u dot, this w dot are the accelerations. Okay, and this other parameters are known. So we can see that once the aircraft is here and we have disturbed this aircraft from given direction, like here, this is the x direction. Here aircraft is flying in this direction, and some disturbance is given in this direction. This you can see here that after disturbance, if the aircraft is going in such a way that this is the amplitude and this is the time, with respect to the time, if you see the plot 1, it is increasing slowly, it is coming down, and after some times you can see here it is on this line. So it is stabilized here and reached to the equilibrium position. If you see the plot 2, which is shown by the red ink, so this plot, as and when we have disturbed, after disturbance the amplitude of the oscillations are increasing. For every time it is increasing and increasing, and it is diverging, it is not converging. Okay, so it is unstable. And third case, which is neither increasing nor decreasing and maintaining the same amplitude, this is called the neutral stable. So here we have one case, the case 1 is a stable, dynamically stable, case 2 is dynamically unstable, and case 3 is dynamically neutral stable. So we can see that aircraft is in this configuration, and we should try to make that aircraft oscillation should decrease with passing of the time. Now we can see these are the equations of motion in perturbed form, and it is we can proceed with equation of motion as first equation. We know that it is a x direction equation, and this is the mu dot is equal to minus mg cos theta 1 plus q1 bar q1 s minus cdu plus 2 cd1 u by u1 minus cd alpha minus CL1 alpha minus CD delta E into delta T. This is the equation number 1, which is the perturbed equation for x direction. Now if you take the second equation, which is the motion in a z direction, which is m, w dot minus q1 u1 q is equal to mg theta plus q1 bar s minus cl alpha plus 2cl1 u by u1 minus cl alpha plus cd1 into alpha minus cl alpha dot c bar by 2u1 minus cl q c bar by 2u1 minus cl delta alpha into delta alpha. So this is the force equation in z direction, and third one is the moment equation, which is a pitching moment with respect to the lateral axis. So this equation, we can say that Iyq dot is equal to q1 sc bar cmu plus 2 cm1 u by u1 plus cm alpha into alpha plus cm alpha dot into alpha dot c bar by 2u1 plus cm q c bar by 2u1 plus cm delta E into delta E. So this we can write in the form of that this u dot is equal to minus mg cos theta 1 plus, here we can write that this is a full xu, so xu dot u plus x alpha dot alpha plus x delta E into delta E. So here we have made all other parameter as a x sub u and sub alpha dot and sub delta E. Same way, the second equation we can make that w dot minus u1q is equal to minus g theta plus zu dot u plus z alpha dot alpha into alpha plus z alpha dot, this is the dot into alpha dot plus z q into q plus z delta E into delta E. We all know that this delta E is a elevator deflection, q is a pitch rate, and alpha dot is a rate of change of angle of attack. So here xu, x alpha, zu, z alpha are dimensional derivatives. Okay, so we have to make, we can write that this q dot is equal to mu dot u plus m alpha into alpha, m alpha dot into alpha dot. This is a moment equation in perturbed form, plus mq into q plus m delta E into delta E. Here xu, xl, zu all are the dimensional derivatives. There are the equations of motion with perturbed u dot, w dot and q. So these are the equation, and this shows the acceleration of the aircraft in x direction, z direction, and the moment in this pitch rate in lateral axis. Here we can write this all, this force in u direction, that is xu is equal to minus q1s by m minus cdu plus 2 cd1 plus u1, and this we can use the Laplace transformation. So we can define the function fs 0 to alpha e to the power minus st ft into dt, and this L x dot is equal to s xs minus x into 0. We can assume that this x is equal to 0. So this is a first order differential form in linear pattern. We can also write the equation of motion as su s is equal to minus g cos theta 1 theta s plus xu us plus x alpha alpha s plus x delta E into delta es. So we are transforming these three equations. We can write in the matrix form s minus xu into us minus this in the second column minus x alpha into alpha s plus g cos theta 1 theta s. This is equal to x delta E into delta es. Same way we can write all these three equation and putting the value qs is equal to q is equal to theta. So putting all these things in the matrix form and removing us, alpha s and all other terms, we can get the equation in this matrix form that s minus xu minus x alpha plus g cos theta 1 minus zu s u1 minus z alpha minus zq plus u1 plus g cos g sin theta 1 minus mu minus m alpha dot s plus m alpha s square minus m q sub s us alpha s and theta s, and this will be is equal to x delta e into delta es, z delta e into delta es, m delta e into delta es. So here this delta e is a control requirement of elevator. So now finding the characteristic equation and then finding the roots and determinants, we can decide the aircraft is dynamic stable or not. So here if we take the determinant and if we make it 0, we'll give the characteristic equation. Let's see the equation here. As to power 4 plus bs to power 3 plus cs square plus ds plus e is equal to 0. Here we can get from the previous matrix that determinants part, we can get that a is equal to u1 minus z alpha, b is equal to minus u1 minus z alpha dot, xu plus mq, and c we can get minus z alpha minus m alpha dot, u1 plus zq, e is equal to, we can get g cos theta 1 m alpha zu minus z alpha mu plus g sin theta 1 mu x alpha minus xu m alpha. So solving these equations depending upon the root, we can say that the system is dynamic stable or not. So if we solve this equation, we can find out that aircraft is static stable or dynamic stable, whether the aircraft is stable or not. By seeing this equation, we can find out that aircraft is dynamically stable or not. So this is these are the references which we are taking from the Robert C. Nelson, Aircraft Stability and Control, then NPTEL lectures from the professor. And thank you very much for joining the session. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.